And if the white dwarf is already near a different kind of threshold in mass, a threshold first calculated by the brilliant Indian astrophysicist Subrahmanyan Chandrasekhar, he noted that if you have a white dwarf that's near a limit, what limit is that? About 1.4 times the mass of the sun, and you drop some more material on it, it's no longer just let's explode the outer surface. The entire star, white dwarf, goes unstable, and it collapses and becomes a supernova.
So why can adding something as small as a planet's worth of mass to a dead star cause it to annihilate itself in a single flash? A white dwarf, roughly the size of Earth, can quietly hold more mass than the sun. Yet, if you push it just a bit too far, every atom inside suddenly loses a contest against gravity. That too far is not vague, it is a sharply defined limit, and limits like that do not only decide the fate of white dwarfs. They set whether a collapsing star becomes a neutron star, a black hole, or tears itself apart in a supernova, and they exist for deep physical reasons, not cosmic drama. The basic idea underneath all of this is simple: balance. Any star is a tug of war between gravity pulling inward and some kind of pressure pushing outward. In an ordinary star like the sun, that outward pressure comes from hot gas, particles moving fast and bouncing off one another. The hotter the gas, the stronger the push. This is called thermal pressure, and it keeps the star from collapsing for billions of years. But when the fuel runs out and the star cools, thermal pressure fades. The surprising thing is that dead stars can still stay up, not because they are hot, but because the rules of quantum mechanics refuse to let their particles be squeezed in just any way. The first surprise is that in a white dwarf, the main support against gravity is a purely quantum effect. Inside, atoms are crushed so tightly that electrons are no longer bound to individual nuclei. They form a dense sea of electrons. Electrons obey the Pauli exclusion principle, which says that no two electrons can occupy exactly the same quantum state at the same time. When you try to squeeze them into a smaller volume, you're forced to pack them into higher and higher energy states. That packing generates a pressure that does not depend on temperature, called electron degeneracy pressure. It means a white dwarf can be very cold and still resist gravity. But there's a catch. As you pile on more mass, the electrons have to move closer to the speed of light to provide enough pressure. Special relativity then limits how much extra push they can give. Beyond roughly 1.4 times the sun's mass, adding more material makes gravity increase faster than degeneracy pressure can respond. At that point, no static balance is possible, and the star has crossed a fundamental stability boundary. So, what actually happens in the moment a white dwarf crosses that invisible line? Once it goes over the limit, there is no nearby configuration where gravity and pressure can match. The entire star begins to contract, and the increasing density raises the temperature of its interior through compression. That heating ignites runaway nuclear fusion in material that had long been dead, especially carbon and oxygen packed into the star's core under degenerate conditions. Instead of a gentle restart, the fusion rate skyrockets because higher temperature makes fusion easier, which releases more energy, which heats the gas further. This runaway process unbinds the star in a thermonuclear supernova, leaving almost nothing behind. The mini reveal here is that because the physics of this thermonuclear runaway tends to produce similar amounts of radioactive nickel in each event, these supernovae reach nearly the same peak brightness, with only modest, well-understood variations. Astronomers use them as standard candles to measure distances across the universe and to discover that cosmic expansion is accelerating. But gravity has another move. It can squeeze matter into an almost pure sea of neutrons. If a collapsing core does not explode completely, but has enough mass, the pressure grows so enormous that electrons and protons are forced to combine into neutrons through reactions that emit ghostly particles called neutrinos. This produces a neutron star, where matter is packed far beyond white dwarf densities. A teaspoon of neutron star material would weigh around 1 billion tons on Earth, a figure inferred from combining observed neutron star masses with their tiny radii, only about 20 kilometers across. Neutrons, like electrons, obey the Pauli exclusion principle, so they generate neutron degeneracy pressure. that can halt collapse for cores up to about 2 or 3 times the Sun's mass, according to calculations using general relativity and nuclear physics checked against observed neutron star masses. Beyond that, even neutron pressure is not enough. There's again no stable configuration, and the result is a black hole. Rotation adds an even stranger twist to these limits. A rapidly spinning neutron star experiences an outward centrifugal effect that partially counters gravity, especially near the equator. The faster it spins, the more mass it can support without collapsing, a prediction of relativity and fluid dynamics confirmed by observing extremely fast spinning pulsars. Over millions of years, as the star radiates energy, it gradually spins down. That means a neutron star that was once safely below its maximum mass could, in principle, cross the stability line later in its life and collapse into a black hole long after its birth. Stability is not just about where you are now, but about how your properties, like spin, slowly change with time. At this point, it is natural to ask whether a black hole is really a new kind of object, or simply what happens when gravity finally wins every possible negotiation. In general relativity, gravity is described not as a force in the usual sense, but as curvature of spacetime itself. For a given mass, there is a particular radius, the Schwarzschild radius, within which spacetime is curved so strongly that all possible paths a particle can take lead inward. And the boundary of this region is the event horizon, where the escape speed equals the speed of light. Cross that, and no signal can get back out. The threshold is again sharp. Just outside the horizon, light can still escape. Just inside, it cannot. Here is the counterintuitive part. For a distant observer, clocks falling toward the horizon appear to slow down and never quite cross it. Yet, for the falling object itself, crossing the horizon happens in finite time, and, for a large black hole, without any violent local signal. The boundary is absolute in the global geometry of spacetime, not in any sudden change of local forces. All of this brings us back to the original puzzle of tiny extra mass causing catastrophic change. The answer is that the laws of physics only allow stable resting points for stars in certain mass ranges. Those resting points are where inward gravity and all available outward pressures, thermal, electron degeneracy, neutron degeneracy, and even rotational support, can exactly balance. When you add mass and push a star past the last available balance point, the system has no nearby quiet state to settle into. Like heating water from just below boiling to just above, you get not a slightly hotter liquid, but a new phase entirely. Vapor in one case, neutron star or black hole in the other. The universe, which looks smooth on the surface, is built around these hidden cliffs in the space of possibilities. Our sun sits comfortably far from the thresholds that would make it explode or collapse, which is why life on Earth has had billions of years of relative stability. But the same sharp limits that spared us also created the supernovae that seeded the cosmos with heavy elements. The deeper question is how many other invisible thresholds, written into the same underlying laws, are still waiting to shape the universe's future in ways we have not yet imagined. Like, if this was interesting, hit the subscribe and turn that notification bell on for more.